So, good morning, everyone. We have discussed in the previous classes regarding the measurement of AC circuits, how three-phase AC circuit is being measured and its applications. After that one, we are now discussing regarding magnetic circuits. Okay. So, in electrical, we basically have two types of appliances, like one which converts electrical energy into magnetic energy, then again into electrical energy. The other one is one which converts electrical energy into magnetical energy, then to the mechanical energy. So we have the first one is transformers. First one is transformers. Transformers. So these are electromagnetic. Electromagnetic. In transformer, electrical energy is converted into magnetic form and then from magnetic form into electrical form. This is for the purpose of isolation, as we can obtain the isolation between primary and secondary. The other one is motors or generators. Generators. This basically converts electrical energy into mechanical energy with in-between conversion of magnetic. So we have electrical. So we have electrical domain. Electrical domain. We have magnetic domain. Magnetic domain. Then we have mechanical domain. Mechanical. The study between electrical domain, the conversion of energy between electrical domain and magnetic domain is electromagnetics. Electromagnetics. So let us say we have a source. Let us say we have a source. We have an electrical source. We have a source. Source energy being transferred from source to a load. Energy being transferred from source to a load. Okay. So in between, the energy can be lost. Energy can be lost or dissipated in resistor. Energy can be lost or dissipated in resistor. Or energy can be stored. Energy can be stored in inductors. Energy can be stored in inductors or capacitors. Or energy can be transformed. For going to the load, energy can be transformed to another domain. Energy can be transformed to the another domain. Okay. So in this case, we are considering magnetic domain. In this case, we are considering magnetic domain. Okay. So we know that all the domains have kinetic and potential variables. All the domains have kinetic and potential variables. In electrical domain, we have potential variable, a voltage. A voltage is a potential variable. Potential difference between 2 points is voltage. And the kinetic variable is current, I. Voltage is in volts and current is in amperes. Okay. A kinetic variable is current I. Okay. Because the rate of the flow of charges produces current. Similarly, in magnetic domain, in a magnetic domain, we have potential element MMF, a magnetomotive force, and the kinetic domain is not flux, it's rate of change of flux. Kinetic domain is rate of change of flux, that is d phi by dt. So d phi by dt is similar to the current in the electrical domain, and MMF is similar to the EMF or voltage in the electrical domain. So this study of electromagnetics is basically for transformers. As I told, study of electrical domain is for studying or observing transformers. What are transformers? Transformer is a device which converts electrical energy from electrical domain into magnetic domain. So we have magnetic domain. We have electric domain. We have electric domain in the primary, and we have electric domain in the secondary. So this transformer In the primary of the transformer, we have electric domain. In between, it's converted into magnetic domain. In between, it is converted into magnetic domain. Then again to the electric domain. Okay. So this is electromagnetics. This is electromagnetics. Electromagnetics. Okay. So let us first study what is a transformer. Then the laws of electromagnetism, electromagnetics or electromagnetism. There are laws of electromagnetism. Let's go through the laws of electromagnetism, how the electrical energy is being transformed to the magnetic energy, and what is the relationship between magnetic field and the current. What is the relationship between magnetic field and the current? These we study during laws of electromagnetism. So a transformer is made up of two parts. A transformer is made up of two parts. First one is a magnetic core. First one is a core which is made up of a magnetic material. Magnetic material, generally ferrite or iron. Ferrite or iron. Core must be ferrite or iron core. It must be magnetic in nature. So in order to the magnetic field will be created inside the core. Therefore, the core must be magnetic. The other one is we have coil. We have coil. Coil is of copper. For the flow of, we have coil. Copper coil. We have coil. Copper coil. Okay. So the core is magnetic and the copper coil is electric. Okay. So there will be a flow of current. In this is primary. This is primary. And this is secondary. Primary is connected to a source. As you know, this primary is connected to a source, electric source, and there will be a flow of current in the primary side of the coil. There will be a flow of current in the primary side of the coil. This flow of current will, in the magnetic domain, it will create a magnetomotive force. It will create a motive force. Basically, it will create a motive force. As it is in the magnetic domain, it will create a motive. It will create a motive force. As it is in the magnetic domain, we call it magnetomotive force. We call it magnetomotive force or MMF. We create a motive force as it is in the magnetic domain. We can call it as magnetomotive force within the magnetic domain. This magnetomotive force, this MMF will set up a flux. This MMF will set up a flux. This MMF will set up a flux. This flux will induce an EMF, secondary EMF. This flux will induce a secondary EMF, induce an EMF in the secondary coil. This flux will induce an EMF in the secondary coil, and that EMF in order will be creating the flow of current in the secondary coil, that is I2. So basically we will be having I1 in the primary coil. This flow of current will induce a magnetomotive force in the magnetic domain. This magnetic force, magnetic field will be created in the coil, in the ferrite core. That's why this core should be of magnetic. This induced magnetomotive force will set up a flux. That flux, the rate of change of flux, will induce an EMF in the secondary coil. So that EMF is of electric. So basically we are converting electric domain, the power energy from electric domain into the magnetic domain, then again to the electric domain. So this is what is electromagnetics. This is what is electromagnetics. So there are laws of electromagnetics. There are laws of electromagnetism. Basically, or we generally call it as Faraday's laws of Faraday's laws of electromagnetism. Because it links between the induced EMF in the electrical field, in the electrical domain, to the flux, or to the rate of change of flux in the magnetic domain. The Faraday's law links between the induced EMF in the electric domain or and the flux in the magnetic domain. So we have laws of electromagnetics of Faraday's laws of electromagnetism. So we can write it as the induced voltage or any voltage V, induced voltage or the setup voltage V will be equal to N into d phi by dt. N into d phi by dt. This is voltage. This is voltage. This is number of turns. This is voltage. This is number of turns. And this is rate of change of flux. Rate of change of flux. So this is how we are linking the induced voltage or applied voltage. This can be induced voltage or applied voltage. If it's induced voltage, the rate of change of flux will be because of the applied voltage. Or if it's the induced EMF, it will be because of the rate of change of flux. So the induced EMF will be equal to the number of turns into the rate of change of flux. Apart from this, we can also link the magnetism and electricity. We can also link magnetism and electricity. The current, in terms of current, we can also link between the current flowing through the conductor and the magnetic field produced across the conductor. So that can be done by using Ampere's law. Electricity and magnetism. Electricity and magnetism. So you know that the SI unit for current is ampere. Okay, this is given in the name of Andre Marie Ampere. This is given in the name of Andre Marie Ampere, a French scientist. Okay, French scientist on whose name we have this law, Ampere's law. So basically, what he observed, he placed two current carrying conductors. He placed two current carrying conductor on a table. Okay, so when he placed two current carrying conductors, he observed that as if the two current carrying conductor, the current is in the same direction, they attract each other. There are two current carrying conductors. If they are in the same direction, they attract each other. And if the two current carrying conductors are placed, one is carrying current in one direction, the other one is in opposite direction, they repel each other. This is what he observed, and he tried to deduce why the two current carrying conductor attract each other and two current carrying conductor in the opposite direction repel each other. So what he observed is when we have a current carrying conductor, there will be a magnetic field induced across the current carrying conductor. There will be a magnetic field. If you consider it three-dimensional, there will be a magnetic field across that current carrying conductor. Okay, there will be a magnetic field across that current carrying conductor. This magnetic field can be when we have a current carrying conductor, the induced magnetic field, the direction of the magnetic field can be described by using right hand thumb rule. So let us say this is a current carrying conductor and I have my thumb placed like this. So if current carrying conductor, the thumb is like this, the current is in the direction of the thumb, the induced magnetic field will be in the direction of the other fingers pointing. That means if you have a current carrying conductor like this, there will be a magnetic field induced in this direction of the other fingers. This is right hand thumb rule of a current carrying conductor. So he observed that the induced magnetic field, the magnetic field induced by the current carrying conductor, it will be in the direction of the other fingers when other fingers compared to the thumb. Okay, so the flux density in a magnetic field, the magnetic field can be described in terms of two quantities. They are flux density and magnetic field intensity. in terms of two quantities. They are flux density and magnetic field intensity. Okay, the flux density can be defined as flux lines passing through a unit area. So if you have a unit area, the number of flux line passing through that unit area can be defined as flux density. It is generally denoted in B as flux density, and the SI unit is as flux number of flux lines is in Weber and unit area is in meter square. The unit for flux density is Weber per meter square. Okay, and magnetic field intensity can be defined as force experienced by a unit north pole. Force experienced by a unit north pole when placed in a magnetic field. Let us say if we have, we know that the north pole and south pole cannot be segregated from each other. Any magnet will have both the north pole and south pole. However, for the sake of assumption, if we place a unit north pole in a magnetic field, the force experienced by it can be defined as magnetic field intensity. It is generally magnetic flux density will be dependent on the medium, and magnetic field intensity denoted as H is independent of the medium. Okay, so this is independent of the medium. Therefore, the magnetic flux density B can be correlated with magnetic field intensity in terms of mu and mu H. B is equal to mu and H, where this is magnetic flux density and this is magnetic field intensity. The mu is the permeability of the medium. Mu is the permeability of the medium. Mu can be written as mu naught and mu r. Mu naught and mu r. Mu naught is the permeability of the free space. Mu naught is the permeability of free space. Permeability of free space, and mu r is the relative permeability, and mu naught is equal to 4 pi into 10 to the power of minus 7 Henry per meter. 4 pi into 10 to the power of minus 7 Henry per meter, and mu r is the relative permeability. In free space, mu r is considered as 1, and every other mediums has their own relative permeability. So the magnetic, so let us say that we have there is a current carrying conductor and there is a magnetic field around the current carrying conductor. So let us say the magnetic field, as we at a particular distance, at the radius, one radius, magnetic field will be equal the B. At we have a current carrying conductor here. So let us say that this distance, the distance is R, radius of the field. At this distance they will have the same magnetic field. That means at this point there will be a magnetic field flux density of B. At this point there will be a flux density of B, and at this point there will be a flux density of B. That means the flux density will be same in this field. So a closed integral of this B dl, a closed integral of this B dl is equal to the permeability mu into I enclosed by that magnetic field. That means this I enclosed. So we can say that the Ampere's law, by using Ampere's law, we can say that the closed integral of the as we know that the magnetic field is produced because of the current carrying conductor, the magnetic flux density, the closed integral of the magnetic flux density as dl is the length of this small areas. We can say that the closed integral of the magnetic flux density and the length, the small area of cross section, it will be equal to mu into I enclosed. We know that B is equal to mu into H, and therefore the magnetic field intensity is equal to magnetic flux density divided by mu. You know that H is equal to B divided by. Therefore, we can also write closed integral of H dot dl is equal to I. Closed integral of H dot dl is equal to I. However, in a closed integral of a circle, we know that closed integral of a circle is the circumference of the circle, and that circumference of the circle is equal to 2 pi r. Circumference of the circle is equal to 2 pi r, where r is the radius of the circle. Where r is the radius of the circle. R is the radius of the circle, and It is the distance between the magnetic field which you are considering and the current carrying conductor. It is the distance between the magnetic field which you are considering and the current carrying conductor. We can also write that H into 2 pi r is equal to I, or H is equal to I divided by 2 pi r ampere per meter. H is equal to 2 divided by ampere per meter. So you know that when the two opposite poles attract each other, and the two uh, similar poles like north pole and north pole repel each other, and the south pole and north pole attract each other. So this is the magnetic field produced by the current carrying conductor is for a wire. So let us consider a solenoid. Okay, let us consider a solenoid. What's a solenoid, or a number of coil? So let us say we have a coil. We have a coil. We have a coil. So it will produce magnetic field in like this, in this directions. The magnetic field will be perpendicular, so it will be producing magnetic field in this direction and in this direction. So there will be a north pole. So if the current is flowing like this, if a solenoid we have, there will be a north pole, and the south pole will be created because of that coil or a solenoid. So let us say if we place, let us say if you place a current carrying conductor, we have a current carrying conductor is placed inside this magnetic field. So this current carrying conductor will also experience the force. So as this current is flowing in this direction and this current is flowing in this direction, this current carrying conductor will experience a force. Because of that force, it will start rotating. This is the basic operating principle. This is the basic operating principle of electrical machines. Electrical machines. So in this class, basically we studied the relationship in electricity and magnetism, which we call it as electromagnetism. There are fundamental laws of electromagnetism, which is proposed by Faraday's law of electromagnetism. Faraday's law links between the electric EMF induced and the reduction of flux. And Ampere's law describes when the magnetic field produced because of the current carrying conductor. Because of when there is a current carrying conductor placed in a magnetic field, it will experience a force. This is the basic operating principle of the electrical machines. So in the next class,